Quantum computing stands at the precipice of a technological revolution, promising to reshape the landscape of computation, information processing, and problem solving. Unlike classical computers, which process information in binary bits, either 0 or 1, quantum computers harness the principles of quantum mechanics, manipulating quantum bits, or qubits, that can exist in superpositions of states. This fundamental difference enables quantum computers to perform certain computations exponentially faster than their classical counterparts, offering tantalizing possibilities for industries ranging from cryptography and materials science to pharmaceuticals, artificial intelligence, logistics, and beyond. At the core of quantum computing's potential lies the phenomenon of superposition, entanglement, and quantum interference. Superposition allows qubits to represent multiple states simultaneously, vastly increasing the computational space. Entanglement, a unique quantum property, enables qubits to be intrinsically linked such that the state of one instantly influences the state of another, regardless of distance. Quantum interference, meanwhile, ensures that only the correct computational paths amplify, leading to the right answers. Together, these properties empower quantum computers to tackle problems considered intractable for even the most powerful classical supercomputers. One of the earliest and most publicized applications of quantum computing is in the field of cryptography. Modern digital security relies heavily on mathematical problems that are easy to compute in one direction but hard to reverse without a key, such as factoring large numbers, which underpins RSA encryption. Shor's algorithm, a quantum algorithm developed in the 1990s, demonstrated that a sufficiently powerful quantum computer could factor large numbers exponentially faster than the best-known classical algorithms, threatening to render many current cryptographic systems obsolete. The implications are profound. Once scalable quantum computers become available, they could potentially decrypt vast amounts of encrypted data, exposing sensitive communications, financial transactions, and personal information. In anticipation of this quantum threat, the field of post-quantum cryptography has emerged, focusing on developing new cryptographic algorithms resistant to quantum attacks. These include lattice-based, hash-based, code-based, and multivariate polynomial cryptosystems, which are believed to be secure against both classical and quantum adversaries. Governments, corporations, and standards bodies worldwide are racing to standardize and implement these new protocols before quantum computers reach the necessary scale to break existing encryption. Thus, the advent of quantum computing not only threatens current security paradigms, but also drives innovation in safeguarding information for the quantum era. Beyond cryptography, quantum computing holds transformative potential in simulating complex quantum systems, a task that is inherently difficult for classical computers. Quantum chemistry and materials science stand to benefit immensely. Many chemical reactions and material properties depend on quantum interactions among electrons, which quickly outstrip the computational power of classical machines as system size increases. Quantum computers, by their very nature, can efficiently simulate these quantum systems, enabling breakthroughs in understanding molecular structures, reaction mechanisms, and material properties. This capability could accelerate the discovery of new drugs, catalysts, superconductors, and advanced materials, ushering in innovations across medicine, energy, and manufacturing. For instance, pharmaceutical companies invest billions in drug discovery, much of which involves trial and error with molecular simulations and laboratory experiments. Quantum computers could model the behavior of molecules with unprecedented accuracy, predicting how potential drugs interact with biological targets, and dramatically reducing the time and cost required to bring new treatments to market. Similarly, in materials science, quantum simulations could lead to the design of novel materials with tailored properties, such as high-temperature superconductors or ultra-strong polymers, by revealing insights into atomic-level interactions that were previously inaccessible. Optimization is another domain where quantum computing promises significant advances. Many real-world problems, from supply chain logistics and traffic management to portfolio optimization and machine learning, involve searching for the best solution among an astronomical number of possibilities. Classical algorithms often rely on heuristics or approximations when faced with such combinatorial explosions. Quantum algorithms, such as Grover's search algorithm and quantum approximate optimization algorithms, QAOA, can explore solution spaces more efficiently by leveraging quantum parallelism and interference. While these algorithms do not always provide exponential speedups, they offer quadratic or better improvements for certain classes of problems, which can translate into substantial practical benefits for industries that rely on rapid, accurate decision-making. In finance, for example, portfolio optimization requires balancing risk and return across a vast array of assets, considering constraints and correlations. Quantum computers could process these variables in parallel, identifying optimal portfolios more efficiently than classical systems. In logistics, optimizing delivery routes for fleets of vehicles, known as the traveling salesman problem, becomes increasingly complex as the number of destinations grows. Quantum approaches could unlock new efficiencies, reducing costs, fuel consumption, and environmental impact. Even in machine learning, quantum computers may accelerate the training of models or enable new types of algorithms that exploit quantum data structures, potentially transforming how we extract insights from massive datasets. Artificial intelligence, AI, intersects with quantum computing in both direct and indirect ways. Quantum machine learning explores how quantum algorithms can enhance tasks like classification, clustering, and regression, potentially offering speedups for high-dimensional data analysis. Quantum neural networks, quantum support vector machines, and quantum principal component analysis are active areas of research, aiming to harness quantum properties for smarter, faster AI. Moreover, as quantum computers mature, they could assist in training classical AI models by rapidly solving subproblems that are bottlenecks in current workflows. Conversely, AI may aid in controlling and optimizing quantum hardware, improving error correction, and automating the design of quantum circuits. Despite these exciting prospects, numerous challenges remain on the path to practical, large-scale quantum computing. Qubits are notoriously fragile, susceptible to errors from environmental noise, imperfect control, and decoherence. The loss of quantum information over time. Building reliable quantum computers requires sophisticated error correction schemes, which often demand many physical qubits to encode a single logical qubit. As a result, today's quantum devices, known as noisy intermediate scale quantum, NISQ computers, are limited in size and fidelity, capable of only modest demonstrations of quantum advantage. Researchers are exploring various physical implementations of qubits, including superconducting circuits, trapped ions, topological qubits, and photonic systems, each with its own trade-offs in scalability, coherence time, and ease of manipulation. Companies like IBM, Google, Microsoft, Rigetti, IonQ, and D-Wave are racing to push the boundaries of qubit count and quality, while academic labs pursue new architectures and materials. Hybrid approaches, combining quantum and classical resources, are gaining traction as a way to leverage current quantum devices for meaningful computations, even as the quest for fault-tolerant, universal quantum computers continues. The development of quantum software and programming languages is another critical frontier. Quantum algorithms require fundamentally different thinking than classical ones, and programming quantum computers involves managing entanglement, interference, and measurement in ways unfamiliar to most software engineers. New quantum programming languages such as Qiskit, Cirq, Qplus, and Qtip are emerging along with simulators and development environments that allow researchers and developers to experiment with quantum algorithms on classical hardware. As the ecosystem matures, educational initiatives and workforce development will be essential to train a new generation of quantum-literate scientists, engineers, and programmers. The economic and societal implications of quantum computing are vast and multifaceted. On one hand, the ability to solve previously intractable problems could unlock trillions of dollars in value, drive scientific breakthroughs, and spur new industries. On the other, the disruptive potential of quantum computing raises concerns about job displacement, security risks, and the concentration of power among those who control the technology. Policymakers, businesses, and civil society must grapple with questions of access, equity, regulation, and ethical use as quantum computing moves from the laboratory to the marketplace. International competition is intensifying, with governments investing heavily in quantum research and infrastructure. The United States, China, the European Union, Canada, Japan, and Australia have all launched national quantum initiatives, seeking to secure leadership in this strategic technology. Quantum computing is viewed as a key enabler of economic competitiveness, national security, and scientific progress. Collaboration and standardization across borders will be crucial to ensure interoperability, security, and the responsible development of quantum technologies. Ethical considerations loom large as well. The power to break existing encryption could threaten privacy, civil liberties, and the integrity of digital systems. The ability to simulate complex biological and chemical systems raises questions about dual-use applications, such as the design of new weapons or bioengineered organisms. Ensuring that quantum computing is developed and deployed in ways that benefit humanity and do not exacerbate existing inequalities or create new risks will require proactive governance, transparency, and public engagement. Looking further ahead, the integration of quantum computing with other emerging technologies could yield synergistic effects. Quantum communication, based on the principles of quantum key distribution and entanglement, offers the prospect of unbreakable encryption and secure networks. Quantum sensors, exploiting quantum coherence and entanglement, promise unprecedented sensitivity in measuring physical quantities, with applications in navigation, medical imaging, and environmental monitoring. The convergence of quantum computing, AI, biotechnology, and nanotechnology could catalyze a new era of interdisciplinary innovation, blurring the boundaries between physical, biological, and digital realms. As quantum computing advances, the very notion of computability and complexity may be redefined. Problems once thought unsolvable may fall within reach, while new classes of quantum problems emerge. Theoretical work in quantum information science continues to uncover surprising connections between physics, mathematics, and computation, deepening our understanding of the universe at its most fundamental level. Quantum supremacy, the point at which a quantum computer can solve a problem no classical computer can feasibly match, has already been demonstrated for specialized tasks, but the quest for practical, broad-based quantum advantage continues. The journey toward widespread quantum computing is likely to unfold in stages. In the near term, hybrid quantum classical algorithms will augment classical systems, providing incremental gains in specific domains. As hardware improves, fault-tolerant quantum computers will unlock exponential speedups for a broader range of applications, transforming industries and scientific disciplines. Ultimately, quantum computing may become as ubiquitous and indispensable as classical computing is today, embedded in cloud services, edge devices, and everyday life. Preparing for this future requires investment not only in hardware and software, but also in human capital, policy frameworks, and international cooperation. Education at all levels must adapt to include quantum literacy, ensuring that the workforce is equipped to harness and guide this transformative technology. Ethical, legal, and social implications must be addressed proactively, drawing on lessons from previous technological revolutions to maximize benefits and minimize harms. In conclusion, the future of quantum computing is both exhilarating and uncertain, marked by immense promise and formidable challenges. Its potential applications span cryptography, materials science, pharmaceuticals, optimization, artificial intelligence, and beyond, with implications for security, economics, ethics, and society at large. As research accelerates and quantum technologies mature, the world must navigate a complex landscape of opportunity and risk, striving to ensure that the quantum revolution serves the common good. The coming decades will test our ingenuity, foresight, and collective wisdom as we unlock the mysteries and possibilities of the quantum realm.